My name is Karan Pandey, and I'm a PhD student at the University of Toronto. Today, I'm going to be talking about Face Extrusion Quad meshes. This work is in collaboration with Andreas Baerentzen and my advisor, Karan Singh. Analogous to sculpting from a block of clay, box modeling workflows create 3D models by extruding and bridging parts from a simple starting shape such as a cube. Hundreds of instructional blogs and videos advocate a box modeling workflow to create quad meshes with well-designed face loops that capture a part structure and follow object flow or deformation lines. Inspired by this artistic practice, we present Face Extrusion Quad meshes, a 3D object representation built on face loop modeling operations that can explicitly mimic a box modeling workflow and properties of artist-designed face loops. For a closed manifold quad mesh, a face loop is a sequence of adjacent quads traversed across opposite edges. As illustrated, a face loop may be self-adjacent or may self-intersect. However, non-self-intersecting face loops are particularly interesting because they can encode structural information by either going around or along features. Artist-designed face loops created via extrusion-based modeling workflows or hours of retopology sessions typically have few self-intersections and are designed to follow object flow lines while implicitly providing a meaningful part structure and object skeleton to the mesh. As you can probably tell by now, not all quad meshes are created equal when it comes to face loop structure. While interactive techniques help artists create clean, well-structured face loop layouts, automatic feature line-driven remeshing typically disregards face loop structures. Here, we see a single face loop in blue traversing all across the shape. Well-designed face loops are often a direct result of using a simple family of atomic modeling operations to create a shape. We therefore restrict ourselves to modeling using 4 atomic operations: the forward operations of extrusion and bridging, and their respective inverses, face loop collapses and bridge separations. In fact, we informally define our face extrusion quad meshes as those that are created or could be created by a combination of extrusion and bridging operations. Given any part structure articulated as a skeleton, we can automatically create an FEQ with a face loop structure aligned to the skeleton using just extrusion and bridging. Our remeshing technique begins by forming quad meshes for each branch node or junction in an input skeleton, and then bridges and extrudes faces on the branch node meshes to form the connectivity of the FEQ. The remeshing method consists of a set of simple local steps, thus avoiding the need for a global search or optimization. As a result, we're able to efficiently construct state-of-the-art skeletal quad meshes in just a few intuitive steps. With the ability to convert a part skeleton to an FEQ, we can create FEQs from any given triangle mesh with just a few additional steps. In particular, we simply first skeletonize the input mesh, or alternatively provide a customized skeleton which articulates the desired part structure on the mesh. We can then construct the connectivity of the FEQ using our extrusion-based remeshing, and finally fit the geometry of the constructed FEQ back to the original shape using a modification of the least squares meshes optimization framework. Here are some results of challenging meshes automatically transformed to FEQs using our remeshing approach. Our constructed FEQs have an implicit part segmentation visualized using colored patches in the figure and a plausible construction history, which we can partially see against shapes in the top row. When compared with prior art in skeletal quad meshing, the design of our branch node meshes helps us adhere better to the symmetries of the shape at junctions and require fewer patches in our quad layout. We also compared the face loop structure of our meshes with that of interactive artist-made quad mesh layouts and feature line-driven remeshing techniques. The face loop structure of our FEQs, visualized here as a skeleton induced by the axis of cylindrical face loops in the mesh, is clearly similar to that of artist-made meshes. On the other hand, we see the extent to which structural information is lost to self-intersecting face loops in the feature line-driven remeshing in the right column. A single large self-intersecting face loop is highlighted in blue for each shape, which is potentially the cause of the unintuitive face loop skeletons in the right. Building an FEQ as a sequence of primitive operations on admissible face loops allows us to encode this sequence of operations as a directed construction graph, which imparts an FEQ with a plausible construction history. We can infer a construction graph for a mesh part by iteratively deconstructing extrusions in the selection while recording each extrusion operation and the relationships between them in the construction graph. The graph can then be used to apply the stored construction history to a given face set, thereby reconstructing the encoded feature or mesh part. An extrusion node in the construction graph contains sufficient information to implement the extrusion operation on any arbitrary closed connected face set. For this, extrusion nodes contain connectivity information, which tells us where to build the extrusions given an initial base face set as input. In particular, the base face set of each extrusion flows into its node, and now, having constructed the extrusion, base face sets of future extrusions flow out, allowing us to continue our traversal through the construction graph. Extrusion nodes further store the geometric information required to build the actual extrusions. At the heart of our geometric representation is a parameterized representation of the face loops in an extrusion. The parameterization is what allows us to recreate the extrusions from arbitrary base face sets. The geometry of a single face loop is encoded using an overcomplete representation of the extruded vertex positions relative to the coordinate frame of each vertex in the base face set. The construction graph allows us to cut and paste parts across FEQs with a lot of freedom. A core part of our contribution is that we do not simply copy a part of the mesh, but rather use the construction graph to rebuild the feature on the target mesh. And since we are rebuilding, rather than simply adding a set of faces, the feature naturally adapts to the shape and connectivity of the target mesh. The construction graph therefore opens up a wide range of possibilities for mixing and recombining features of quad meshes while preserving extrusion connectivity. Artistically, our work can be viewed as the sculpting analog to the problem of imagining a drawing sequence of strokes from a finished sketch. In the figure, we see a complicated feline head cut and stored in a construction graph and then pasted onto base face sets vastly different from the original. We see how the stored construction history adapts to the geometry and connectivity of the target face set and implements the stored operations. While the single face in the one quad base mesh is not enough to accurately reconstruct the feature, we're able to achieve an accurate reconstruction on target face sets both much smaller and larger than the original. Here we present some more modeling applications of our construction history-based cut and paste. In conclusion, we essentially advocate for a modeling framework with a face loop as the modeling primitive instead of single faces. Our framework produces face extrusion quad meshes, which have many desirable properties, such as a clean quad mesh structure, high modularity, and structure awareness. We also outline a simple extrusion-based remeshing pipeline to generate FEQs, which gives highly regular meshes by design, as they are constructed from simple branch node meshes using only extrusion and bridging. Thanks for listening.